Hello, welcome everyone. This is Manish Sharma from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to understand about the datum reference frame. Okay. And the other topic which we are going to discuss today is implied datum and the order of precedence. Okay. So the most important thing in today's session, first of all, we will understand about the datum reference frame. So whenever we take a part, okay. So whenever we take a part, we have to bring this part to a stable condition. Okay, so in this case, you can see in this image, this is a part. Okay, and if this is a part into a space and we want to bring this part into a stable condition, what we have to do, we have to constrain all the movements. Okay, so this if we want to constrain all the movements of this part so that the we can do the machining. Okay, so the machining is accurate. Okay, and the inspection is also accurate. Okay, so whenever the part, let's say this is the part, and we want to I will give you the example. Okay, so we want this part to be in a stable condition. Stable condition. Why we want this into a stable condition? To machining a part or to inspect a part. Okay, so to make this part into a stable condition, we have to constrain the movement of this part. So we have to constrain the movement of the part. Okay, so the if you want to bring the part into a stable condition, then we have to arrest all degrees of freedom. So in this, we have to arrest all degrees of freedom of the part by constrain the part with the reference to the plane. Okay, so we have to arrest all 60. Total, there are 6 degrees of freedom. 6 degrees of freedom. Okay, three are rotational. In this 6 degrees of freedom, three rotational and three are translational. Okay. Now we will understand with the help of 3D overview this thing, because in this explanation, this is very important if you want to bring the part into a stable condition. Okay. So we know that there are 6 degrees of freedom, three are linear movement. Okay. And three are rotary movement. Along the linear movement, totally 6 degrees of freedom are there. In this, you can see, and this is the overview of this. And if you want to arrest all the 6 degrees of freedom, then you have to take the help of datums. Okay. So now we want to take a help of datums. So here I will demonstrate one model. So here I will demonstrate one model over here. Okay. So this is the model. In this model, so here I have a model to demonstrate the datums reference frame. Okay. So in this datum reference frame, I keep this part onto one of the planes. Okay. If the another example, if we take, okay. So in this example, if we are taking, so this is a part. Okay. And this part is having into a space. Okay, so this part can have 6 degrees of freedom. Okay, so this part can move like here in this direction. This part can move in this direction, x y direction. This part can move in this direction. Okay, these are three linear movements. This part can rotate like this into the x direction. Okay, this part can move into this direction, y direction or z direction in this, and the part can rotate like this. Okay, so these three are the rotational movements. This part can be rotated like this also. Okay, so these total 6 degrees of freedom are there in this part. So how we will discuss this? I keep this part onto one of the plane. Let's say if this surface, let's say we are constraining this surface and this surface. Okay, we are mating this surface. So what will happen? The 3 degrees of freedom, we are able to arrest 3 degrees of freedom. Okay, what 3 degrees of freedom we have to arrest? We have arrested in this, if we understand, so the part cannot rotate like this now. This degrees of freedom is arrested. Okay. This part cannot rotate like this. And part cannot move like this. Okay. So two rotary movements and one linear movement is arrested. Okay. So this is how we have arrested the 3 degrees of freedom of this part. Now 3 more are left. Okay. Which are left? 3 more are left. The part can rotate like this. Okay. So the part can rotate like this. Part can move in this direction. And part can move in this direction. Okay. So 2 linear motions and 1 rotary motion is left. Okay. So the 3 degrees of freedom are left and 3 are constrained. Okay. So when we join this surface and this surface of the part. Okay. So if we use this part and join these two surface. So 2 more degrees of freedom are constraints. Okay. Now in this option, 5 degrees of freedom are arrested. Okay. 3 degrees of freedom are already arrested. Now the part cannot rotate like this also. Okay. In the previous section, it can rotate. It cannot rotate like this. It cannot rotate like this. Okay. So all the 3 rotary motions are constrained. The part cannot move in this direction. Part cannot move in this direction. Only one linear motion is left, which is this. Okay. So the part can move only in this direction. So 1 degree of freedom is left. So after constraint, this surface with this surface, and we provide join this surface. Now the part into a fully constrained position. Okay. And logged all 6 degrees of freedom in this. Okay. So part can, so now out of 6, we have constrained all the 6 degrees of freedom. We bring this component to arrest along the, all the perpendicular surfaces of the part. Okay. So what happens? It cannot move in the any direction and rotate in any direction. Okay. Nor it can rotate, nor it can move into any direction, this part. Okay. So when we arrest part of the second datum plane, we constrain 2 degrees of freedom. First, whenever, let's say, this is datum, this surface is acting as a datum. Okay. So this is a primary datum. Primary datum arrests 3 degrees of freedom, 2 rotary motions and 1 linear motion. Okay. Now, this is the second datum, which is the secondary datum. We say this arrests 2 degrees of freedom, 1 rotary and 1 linear motion. And this third is the tertiary datum. Okay, so this tertiary datum arrests 1 degree of movement, which is the linear movement. Okay, so this is how we came this part into a stable condition. So now we can say that this part into a stable condition, and if we want to machine this part, we can machine this part because all the 6 degrees of freedom are arrested. Okay, think like that we are putting a part for a machining onto a table and we have to arrest all 6 degrees of freedom, that the part movement will be arrested. Okay, so this is the most important thing we can learn in this part. Okay, so this is how we can, this is called the datum reference frame. Okay, so what I'm going to do, I will put along this plane. Now what will happen? This movement will be, all the movements are arrested. So whenever we have a plane surface, okay, so in this condition, this surface, if we want to arrest all degrees of freedom, we have to keep on primary plane and secondary and but it on secondary plane and again it on tertiary plane. Okay, so this will become an stable condition. So the first surface what we take for resting primary datum is called the primary datum. First surface is called the primary datum. The second surface is called the secondary datum and third surface is called the tertiary datum. Okay, so this is as we put onto the, I will say, feature control frame. So this is how we will put onto the feature control frame. This surface we will write primary datum A. This we will write primary datum B, a secondary datum B. This we will write tertiary datum C. Okay, so datum reference frame is always three mutually perpendicular planes. So in this case, this plane, and this plane, these three planes are mutually perpendicular, and this will become the origin of the measurement. Okay, so this is the very important part. In this, you can see in this also that this plane, and this plane, these three planes are mutually perpendicular to each other. Okay, so if we want to make this part into a stable condition, so we want to arrest all the 6 degrees of freedom of this component. Okay, so in this also you can understand in this example that we have 6 degrees of freedom. This part can rotate in this direction, this part can rotate in this direction, and this part can rotate in this direction. Okay, so these are the three rotary movements. These three are linear movement. This part can move in this direction, this part can move in this direction, and this part can also move in this direction. Okay, so if we want to arrest all the 6 degrees of freedom, first we have to put this surface and this surface join this surface to lock the 3 degrees of freedom. Then we will lock, with the help of secondary datum, we will lock 2 degrees of freedom, and with the tertiary datum we will lock one linear movement which is 1 degree of freedom. So this is how we will all cover the 6 movements of the part. Okay, now we will understand the most important part of this discussion. Okay, and we will move towards the implied datums. Okay, so with the help of this we will understand that what is called the implied datums. So in this particular session of GD&T, we are going to discuss about implied datum also. Okay, so what is implied datum? To understand this, we want one example. Okay, so in this example you can see that this is a part, drawing. In this part drawing, the we have provided the dia 7.5 to this hole, and we have provided the tolerance also with the position symbol. Okay, so whenever we are providing the position symbol, uh, these are the dimensions of this hole. Okay, so if we want to check the dimension of this hole, we will follow these two dimensions. Okay, so we have a drawing on which we have a hole. To control this hole, we have a positional tolerance. Okay, so if we want to control this hole, we have positional tolerance. The positional tolerance is not having any datum. So you can see this positional tolerance is not having any datum in this direction. In the third compartment, in the fourth compartment, and fifth compartment, there is no datum over here. Okay, so without datum, if we give a related feature, okay, so this is a related feature, and whenever we give related feature without a datum, then we called it as a implied datum. Okay, so this is very important. I am writing down over here in this part. This is an important point. So if we give a related feature without datum, then it is called as implied datum. Okay, so in this case, we are using the positional tolerance and we are not providing any datums over here. Okay, so this is called the implied datum. So after manufacturing, we may end up the part like this. Okay, so we may end up the part. I will show you into the actual case. Okay, so let's say this is the part. Okay, which we are seeing the drawing. So after manufacturing, let's say this is the part, this is the part drawing we have. After manufacturing, we have manufactured the part like this. Okay, so if we want to inspect this part, that this part is manufactured in a correct position or not, if we want to check the whole position of this part, so what we will do, we do not know which is the primary datum and which is the secondary datum and which is the tertiary datum. Okay, so in this case you can see that we don't know any type of datums in this part, in the implied one. Okay, so in this case we do not have any datums, so we do not know that how to inspect this part. Okay, so what I do is I will rest, let's say if we are taking this condition, so first I will arrest this surface to this surface. Okay, so the 3 degrees of freedom will be arrested. Now what will happen, I will lock this surface and the this second one. Okay, and let's say if somebody will check, I will make this position also to lock this properly. Okay, we are just coinciding, and the this is how the 5 degrees of freedom are arrested. Okay, so I am taking primary datum this surface and secondary datums this surface. Okay, then I will arrest this point to the this surface. Okay, so you can see that now I have arrested all the 6 degrees of freedom. Okay, so first what I have taken, primary datum, secondary datum, and tertiary datum. Okay, when I have not provided in this drawing, if I have not provided any references, okay, in this case I haven't provided a primary datum, tertiary, secondary datum, and tertiary datum in the fourth, fifth, and sixth compartment. What will happen? Whenever the inspector who is inspecting this part, somebody will check like this. Okay, somebody will check like this. In this, you can see there is a gap. Okay, there is a gap over here. So when I am using primary datum this, secondary datum this, and tertiary datum this, the gap is over here. Okay, so the position of the hole will be different. Let's say if another person comes, okay, and he is also going to check this part. He is going to inspect this part. If I will delete all these, okay, just to show you, let's say some other inspector came and checked this part. Okay, that this part is manufactured correctly or not. So firstly this he makes this datum with this surface to this surface and locks the primary datum. Okay, and this surface he uses as a secondary datum. Okay, previous person used this surface as a secondary datum, but the another second person uses this surface as a secondary datum. Okay, now, okay, let's say if I will join this properly. Oh, sorry, not like this. If I will join properly, sorry, this, okay. So this he uses as a secondary datum, and this surface, this part, this perpendicular surface, he uses as a tertiary datum. Okay. Now you can see what happened over here. Previously the gap is coming over here in this plane, gap is coming over here. So the hole, if somebody measure this hole from this datum to this, it will come different value. And this time the second person who measures, the gap is coming over here. Okay, so somebody will measure now, this the value will be different. Okay, so you can see that if we are not providing the datums into the drawing, if we are not providing to a related feature into a drawing, let's say if we are not providing any datums over here, so although this is called the implied datum, but this is not the correct way. Okay, in this way the inspector is confused that which surface I have to take it as a primary datum, which surface I have to take it as a secondary datum, and which surface I have to take it as a tertiary datum. Okay, now Okay, now what will happen if in this case I will provide datums. Okay, so in this drawing, now you can see now with the this what happens, the x and y direction. In the x and y direction, I have given this, okay, datums. So from ASME by 14.5 1982. Okay, so in 1982 ASME by 14.5, in 1982 standard, we are not supposed to give implied datums. From 1982, previously we used the implied datums, but from 1982 standards, we are not supposed to give the implied datums for such applications. Okay. So from 1982 by 14.5 standards, we are not able to provide the implied datum onto the engineering drawing. Okay. So this is very important part. Now, in this drawing, you can see that this back surface, I have used it as a primary datum. Okay, for this part. This surface, this second surface, I have used it as a secondary datum. And this surface, this bottom surface, I have used as a tertiary datum. Okay, so here you can see that primary datum, secondary datum, and tertiary datum we have provided. Okay, onto this part. So first, I will put this part along the way to the surface. Then I will make this surface onto the secondary datum and log the movement. And then I will put the tertiary movement. Now the steps are being, for the inspector, all the steps are being given that this is the primary datum, this is secondary datum, and this is tertiary datum. So the confusion for the persons is eliminated. Okay. So whenever the inspector will come, he will check the drawing and he will see that which is the primary datum, secondary datum, and tertiary datum. Okay. Now, the most important part over here is you can use the primary datum, this also, and this also. Okay. So in this case also, that you can give like this. If I will make 1 second. Okay. So if I give like this, so in this I can also give, sorry, I have made it smaller. Let's say I will make a little bigger. In this I can also give like B, A, C. Okay, so what will happen when I will give this way? So first of all, the inspector come and this they uses as a primary datum, this surface as a primary datum, because I have given B in the first position, and the first position is for the primary datum. Okay, so this is the primary datum. Then A. Okay, so this surface he uses as a secondary datum. Okay, and this surface, which is C, we are using as a tertiary datum. Okay, so this is called the order of precedence. Okay, if we are using ACB, BAC, or ACB or ABC, okay, whatever we are choosing, so this is called the order of precedence. Okay, so whatever we are giving as per the manufacturing applications, okay, as per the applications, then we see what is going to be happen like ABC or ACB. This is called the order of precedence depending upon the functionality and the assembly requirements. Okay, so whatever will be the functionality of the part, what will be the assembly requirements of the part, we have to decide whether we are going to use ABC or BCA, BAC or ACB. Okay, so whatever we are going to use, it will be depending on the requirement of the function and the functionality of the part. Okay, so this is all about the datum reference frame, implied datum, and order of precedence. Okay, in the next session, we are going to cover in detailed manner about the datum types. Okay, so thank you all of you. In the next session, we are going to learn some more topics of geometric dimensioning and tolerancing. Thank you.